Greetings, my friend. Welcome back to Space Enjoyer. In the first series of this video cycle, we examined the process of protostar formation from a gas dust cloud due to gravitational contraction. We have understood why stars mostly appear in groups in the form of star clusters. The number of stars in clusters, according to our estimate, should be about 1000 if we take into account the mass of the cloud we found and assume that eventually stars with masses close to the solar one are formed. In addition, it is possible to understand why the masses of stars are enclosed within relatively narrow limits, inevitably associated with the Jeans criterion. When the heating of the central condensation turns out to be sufficient for the increased gas pressure to resist gravity, the compression of this central condensation stops. And here, the main process is the accretion of matter from the gas shell to the formed core. As a result, the mass of the core is gradually increased. With increasing mass, the luminosity of the nucleus also grows rapidly. At this stage, the protostar is isolated from the external environment by a dense and opaque shell for visible radiation. Such objects have received the figurative name of cocoon stars. They process the hot radiation of the protostar inside them into powerful infrared radiation. With a further increase in mass and luminosity, the rapidly increasing radiation pressure of the protostar stops accretion and then begins to repel the remnants of the shell that didn't have time to fall on the nascent star. This circumstance allows us to estimate the luminosity of a young star in a similar way as we did in the case of gravitational instability. At the moment when accretion stops at the boundary between the star and the shell, the force of light pressure is balanced by the force of gravity. Therefore, the critical value of luminosity is determined by the condition under which the radiation force is equal to the inverse force of gravitational contraction. If the luminosity of the star is L and its radius is r, then the radiation flux through the unit surface area is L divided by 4p r squared. With an absorption coefficient per unit mass of kappa, a test element of a unit volume will absorb the energy of kappa rho L divided by 4p r squared per unit time. To obtain the momentum of absorbed radiation, which determines the strength of the light pressure, this expression must be divided by the speed of light c, since a photon with energy h nu has an impulse h nu divided by c in the direction of propagation. Then we can write the following expressions for the force of light pressure and the gravitational force. Then, from the equation given above, we obtain the limiting value of the luminosity. This value is commonly called the Eddington limit of luminosity. In the depths of stars, where matter is almost completely ionized, Thomson scattering by free electrons plays an essential role, for which the scattering coefficient sigma equals to 6.7 multiplied by 10 in the power of minus 25 square centimeters. It corresponds to the lowest possible opacity of a fully ionized substance. Therefore, to estimate the maximum possible luminosity, we can take the value kappa equals to 6.7 multiplied by 10 in the power of minus 25 and divided by the mass of a single hydrogen atom. Then kappa will be about 0.4 square centimeters per gram, and for the mass of 100 solar masses, the limiting luminosity of a star can be estimated to 3 multiplied by 10 in the power of 6 solar luminosities. This estimate corresponds well to the luminosity of the brightest known stars. The powerful radiation of the core, which stops accretion with its light pressure, disperses the shell and clears the space around the newborn star, as if blowing the remnants of the shell into the interstellar medium. At the birth of a very massive and bright star, this process can generate a shock wave, a sharp compression of plasma propagating in the parent gas dust nebula, and lead to new, further processes of star formation. In this case, a Herbig Haro object may be formed. In addition, if the cloud was initially rotating, the protostar may still have a protoplanetary disk consisting of matter that has not accreted onto the star, and it may subsequently evolve into a planetary system. The newborn star itself at this time passes into a hydrostatically equilibrium state due to the fact that with a sufficiently large mass, a new own energy source is turned on in its bowels. This source is thermonuclear reactions. At this time, the star finally switches to the main sequence, on which it remains most of the time of its life. Amount of evidence of stellar evolution, including its earliest stages. Stars are born literally before our eyes. For example, globules are small dark gas dust nebulae in which the process of gravitational contraction is possible or has already begun. The mass of globules can reach 100 solar masses with a particle concentration of from 10 in the power of 4 to 10 in the power of 6 particles in cubic centimeter, and size of the order of 1 parsec. Herbig Haro objects are observed in some globules. These objects are star-shaped clusters with an emission spectrum. They were first discovered in the Orion Nebula in 1954, although they were absent from photographs a few years before. This was one of the first directly observed consequences of the star formation, taking place literally before our eyes. It's assumed that they are associated with dense gas condensations, which are hit by a supersonic stream of stellar wind from the source of star formation. Sometimes Taurus type stars are observed in globules, which apparently are less massive than young stars associated with Herbig Haro objects which have not yet completed the process of their gravitational contraction. Unpredictable changes in luminosity, which have no regularity, are characteristic of Taurus type stars. Flare stars of the UV Ceti type are found in those areas where there are variable Taurus type stars. They are distinguished by the extraordinary speed of luminosity increasing during episodic flashes. In less than a minute, the radiation flux can increase tenfold. After that, it returns to the initial level within about an hour. Another type of protostar are FU Orionis, which increase their luminosity tens or hundreds of times over a period of 6 months to 30 years. They are distinguished by powerful infrared radiation and the presence of lithium lines in the spectrum. This suggests that thermonuclear reactions in these stars have not yet begun. This concludes my story about protostars. In the next episode we will talk about stars at the stage of main sequence, where they spend most of their life cycle. Thanks for your attention. If you like such videos, please leave a like, subscribe to the channel, and we will meet again soon.